Hello and welcome to the ECE 10 final review session. I'm going to get started with some key topics from the ECE 10 course. So we're going to do a brief pre-midterm topic review and then talk about some circuit responses with initial conditions and LTI systems and how you can use that to compute various inputs and outputs of your circuit with respect to an input tone. And then we'll take a look at sinusoidal steady state, impedance and admittance, complex power, and energy and quality factor, which are all post-midterm topics. So just a brief review of pre-midterm topics. You should have a pretty firm grasp on these by now, but voltage is defined by 2 points. When you select a voltage polarity in a problem, you want to stick with the voltage polarity that you've selected. Any sign convention you choose is fine as long as you're consistent with it. And then for current, it only flows through a closed loop. So if you have an open port, there isn't going to be current flowing through that branch. So again, current direction is arbitrary, but it does correspond to the voltage across something. So you might want to choose it in a logical way such that the current is flowing from positive to negative. But again, it is a bit arbitrary in this choice. And then power is the product of voltage and current. It is a time-dependent component when you have time-dependent voltages and currents. And again, direction matters. If you're looking at a component that is delivering or absorbing power, you want to make sure that you're getting the correct sign for your result. So for example, if you have a voltage source and it's delivering voltage to the circuit, you don't want to end up with a sign that would indicate that the source is absorbing power, because with the result that you should get should match with the physical reality of the circuit. And this is just a little summary of various different equations that you might use on the final. Obviously Ohm's law and the voltage and current relationships for the different components, and also series parallel combinations. You might also see this with impedances as well. So series and parallel combinations also apply for impedances. So it's important that you know how to do that as well. Impedances in general act like resistors. And resistors are power dissipating components, whereas ideal inductors and capacitors only store energy. They don't dissipate power. And so just check to make sure that everything adds up correctly in your circuits if you're looking at energy and power in a question, to make sure that all of your components are functioning based on their physical realities. And then Kirchhoff's laws, you should be familiar with that. And Thevenin and Norton. And finally, superposition is a method of solving circuits. And so this might be something that you see on the final. In fact, we're going to do an example on it because it has appeared in the past. Now moving on to topics that are post midterm in this class. So this is going to be looking at some circuit responses, initial conditions, and LTI systems. So if you're currently taking 102, some of this may sound a bit familiar as well from that class. So in terms of circuit responses, there's the zero state response where all initial conditions are zero, but you have an input. So this is going to mean that your capacitors and inductors have no voltage or current associated with them when you begin the circuit. It's just due to the input. And then your zero input is going to be just looking at the circuit when you do have some sort of voltage or current initial condition across the energy storing components in the circuit. And so this is going to look at when, like, for example, a capacitor might act as a voltage source for a brief period of time as it discharges an initial current across a resistor or something like that. That's going to be the zero input response if there's no like additional voltage source or anything. And then the complete response is the sum of the zero state and the zero input response. This is true for linear circuits, and in this class, linear circuits are going to be what you're looking at. And then also initial conditions are important because they form the zero input response, so you can't neglect them when you're finding the complete response of the circuit. And so if you're trying to find the initial conditions, you might get a statement that says the circuit has been in a certain way for a very long time. And so that's looking at a DC analysis where the inductor is going to become a wire, the capacitor is going to become an open circuit. And if you don't have like an impulse input, you're going to be looking at the voltage across the capacitor staying the same at 0 minus and 0 plus, and the current across the inductor staying the same at 0 minus and 0 plus. And if you do have an impulse, you will need to integrate from 0 minus to 0 plus. So initial conditions are very important because you want to make sure that you have the correct starting point. This usually involves just going around a circuit. Like if you have a loop, then you want to just do a KVL around the loop and see what the different voltages across the open circuits would be, or if a component is shorted, you want to take that into account because the inductor has been that way for a long time. And then finally with LTI systems, which are the circuits in this class, you can find the complete response by convolving the input with the impulse response. So the impulse response of the circuit is what you get when you just send a plain impulse through it. And so if you have the impulse response, or an earlier part of the question asks you to find the impulse response, then that makes it very easy to deal with if you're later applying a tone to a circuit. So this would be some sort of sinusoid. You can very quickly come up with what the resultant should be based on the general formula that you have. If you're applying a tone to the circuit and you have a frequency response to that tone, then it's going to be just magnitude and the phase. And so this is going to be the impulse response itself. And then if you're just applying a tone to it, then you're going to be just adding in the magnitude and the phase as a result of that single tone. So you might see a sinusoidal steady state question. So in this situation, the circuit must be LTI, and that's going to be majority of your circuits. The input must be a sine or a cosine, some sort of sinusoid. And we have to not really care about the transient response. So if there is some sort of exponential decay, we're assuming that the circuit has been in that position for a long time. All of like the RC time constants have decayed to the point where they're not really impacting the circuit response anymore. And so when we're in this state, we can use the phasor representation of the input and be able to use the network function, which is the Fourier transform of the impulse response, to get the output. And you want to represent all of the equations that you use in the phasor domain when you use this analysis method. You want to be consistent about which domain you're looking at all of your quantities in. And then impedance and admittance. Most important is you remember that admittance is 1 over Z. You may or may not see admittance, but impedance is probably more likely. It's sort of analogous to resistance. In fact, the impedance of a resistor is just the resistance itself, whereas the impedance of an inductor and of a capacitor are dependent on the frequency of the circuit. And so the same rules still apply when you're using impedance. You're just going to be working with complex numbers, and it's going to be looking at sinusoidal steady state, because this version of impedance doesn't take into account any transients in the circuit. So that's important to remember. And then just some terminology. You may or may not see this, but the real part of admittance is conductance. The imaginary part of admittance is susceptance. And since the imaginary portion of admittance is tied to the inductor and the capacitor, if one of those components is dominant, then we call the circuit either capacitive or inductive based on which one is dominant in the circuit. And the imaginary part of Z is called reactance. and it's sometimes specified with an X. Now for complex power, just make sure to have these following equations on your equation sheet. They are results that you should have derived in class at this point. And so just make sure that you have them, because you may be asked to calculate the maximum average power absorbed by a load, and you may be asked to use the matching condition for impedance matching. And so you want to make sure that you just know these two conditions, because you're not really going to want to derive that. And then finally, energy and quality factor. So energy dependent components in the circuit are the capacitor and the inductor. And so since we're dealing with the conservation of energy, then at resonance, you're going to want to have the RLC circuit have the energy across the inductor and the capacitor be the same. And so this is where you can derive your resonance frequency as a result of that by using the equations for the energy of across a capacitor and an inductor and just equating them. And then finally, you learned about the quality factor, or Q. There are three different domains in which Q appears: the time domain, the frequency domain, and the energy domain. And so it's important that when you're using the quality factor, you have the correct domain. So this is going to be the consistent domain that you're using across your problem, or the domain that you shifted into for part of the problem. But it's important to make sure that you're at least consistent, or you're keeping track of which domain you're in, so that you use the correct equation. Now, are there any questions before we move on to some examples? Okay, so I'm going to pause the recording for a few minutes and give you guys a chance to attempt the problem. So now I'm going to walk through the solution to this problem. So we're going to first start with superposition. So superposition is looking at the circuit response to one source at a time. So that means that we're going to turn all of the other sources off in order to only look at the response due to a single source. And now for a DC voltage source, that's going to mean that we're shorting out the voltage source. And for a current source, we're going to be making that current source an open circuit, so there's no current flowing through that part. So we'll start with the 20-volt source. So if all of the other sources are turned off, then the current is going to flow from the bottom across the 20-volt source through the resistor VA, and then both of the 5 amp and the 10 amp current sources are going to be open. So it's going to take the only available path through the 10-volt source, which is now shorted, through the 40 ohm resistor and back to the base of the battery. And so we're going to have a circuit that looks something like this. Which is a bit easier to deal with. So that this is going to be our 40 ohm resistor, and this is going to be our 15 ohm resistor. And so now let's look at the polarity of VA. So the current flows from the 20-volt voltage source into VA. And so this is going to be our positive and negative VA. And so it agrees with a conventional current in this loop. So we are expecting a positive voltage from this source. So this is just going to be a voltage divider. Just call the resultant voltage V1, because it's just going to be one of a number of components of VA. So if we just use our voltage divider formula, we get a result of 5.45 volts. Next, we're going to look at the 10-volt only source and redraw the circuit in that situation. It's going to be very similar. So like the previous case, both the current sources are turned off, and now the 20 volt source is shorted. And so the current is just going to flow through the same outer loop. And this is going to be our voltage VA with the 15 ohm and the 40 ohm. And it's going to be a voltage divider. But instead of the 20 volt source, we're now looking at the 10 volt source. So this is going to be half of the previous voltage. Next, we'll look at the 5 amp source only. So with only the 5 amp source, we're going to see that we have the source, and then we see that the current has 2 paths it can choose. It can either flow through this shorted branch, or it can flow through the resistors. And so if we draw this circuit, it looks something like this. With our 15 ohm resistor and our 40 ohm resistor. And this is our component of VA. But we can look at the circuit and see that the resistive branch is shorted. And so there's going to be no current flowing through it. And that means that there's going to be no voltage across the 15 ohm resistor. And so we can say that this component of the voltage is 0. Next, we have only the 10 amp component. And we can take a look at this source here and see that from this node, there are 2 possible pathways that current can flow. So it can flow through the resistor VA to the base of the current source, or it can flow through the shorted branch through the 40 ohm resistor and then back to the base of the current source. And so that's going to be the resistors in parallel. So this is going to be our 40 ohm resistor, and then the 15 ohm resistor. Now, in terms of the polarity of VA, we see that the current flows into the negative end and exits the positive end, which means that we're going to be expecting a negative voltage from this component. So we can use an equivalent resistance to compute this. So we see that the 2 resistors are in parallel, and there's a 10 amp current entering the branch. And so we have just the product of the equivalent resistance and the amount of current flowing into the circuit. And so this is going to give us negative 109.09 volts. And so with superposition, since we've taken into account sign conventions already, we can just say that VA is the sum of all of the previous voltages that we found for each of the individual sources. So that's going to be negative 100.9 volts. Are there any questions? Okay, so now we'll move on to part B, which is computing VA using node voltage analysis. And so the first thing to do when using node voltage analysis is to pick a reference node. So this is going to be a node that has a lot of branches coming into it, because you want to reduce the number of potential equations that you're trying to solve. And so I've picked this node here, so we'll take this as our ground node and designate this node as V1, this node is V2, and finally this node is V3. So based on the DC sources of voltage sources in the circuit, we can identify some relationships between the nodes. So from the ground reference node to V1, we see that there is a 20 volt source. And so this means that V1 is 20 volts above ground. We can see similarly for V3 that from V2 to V3, there is a 10-volt source. And so that means that V3 is 10 volts above V2. And then we can see that the voltage that we're looking for, VA, this is going to be V1 minus V2, because we're looking at the positive end of VA minus the negative end of VA, based on the given sign convention. Now we can write a KCL in terms of the voltages for node V2. So if we look at V1, so we can look at the 15 ohm resistor branch and say that V2 minus V1 over 15 ohms plus V3 V2, oops, sorry. We can say that there is negative 15 amps going into this node. And then we can say that there is a current I1 flowing out of this node. And so that current I1 comes in here. And so it's important to realize that when we're dealing with ideal voltage and current sources, they may have some amount of voltage across them or some amount of current going through them. And so current can flow through this voltage source and you don't necessarily know how much current is flowing through it. So we're just going to designate it as I1 for this part of the problem. And then we're going to look at V3. And so we can say that V3 over the 40 ohm resistor plus the 5 amps leaving the node, and then minus I1 equals 0. So those are going to be our two equations. And for the purposes of writing the equations, I've just made the assumption that all of the currents are leaving the node that I'm currently looking at, and then adjusted the signs based on which direction I've chosen my currents to be in this problem. So since we don't necessarily know I1, it's a priority to eliminate it from these equations as soon as possible. And we can see we can do that by adding the two equations together. Now we have a single equation and we have a couple of expressions for V1 and V3 in terms of V2 and a constant. And so we can plug these in and combine like terms. And now we have an equation with one variable. And so if you solve this equation, I'm just skipping some algebraic steps, you'll get that V2 is 120.91 volts. And so now we're trying to find our value for VA. And so that's going to be V1, which is 20 volts minus V2. And that gives us our negative 100.9 volts that we got in the previous part of the problem. And so that's a very good sign that we did things correctly. That's something that if you get a problem like this and they have appeared on previous exams, you want to make sure that you're getting the same voltage throughout the problem. And so now we're going to redo this problem using mesh analysis. And so we have 3 smaller meshes here. And so we can designate them I1, I2, and I3. And then we can go around each of the inner loops of these meshes and come up with a set of equations. So if we start going around the first mesh in terms of KVL, we have plus 20 volts. And then we have minus the voltage drop across VA, which is the resistor, and then minus the voltage drop across the 10 amp current source. And then if we go around mesh 2, we have the voltage across the 10 amp current source. And then we have minus the voltage across the 5 amp current source. And then we have minus the voltage across the 40 ohm resistor. And so the way that I've chosen the signs in this equation, if we're going in the direction that the current is being supplied, then the voltage is positive, and if we're going in the against that direction, then the voltage is negative. And then finally, for the third mesh, we have plus 10 volts from the voltage source, and then we have plus the voltage across the 5 amp resistor, 5 amp current source. And so these gives us a set of 3 equations that we can work with. And so if we add these equations together, we get that we get the following equation. So we have 20 minus VA minus the sum of the voltages across the 2 current sources. So the 5 amp current source and the 40 ohm resistor. And then if we simplify this equation using the third equation, we can see that the value across the 5 amp current source is known. We can plug that value in. And then finally plugging in some known values for the resistors and writing things in terms of the mesh currents that we've defined, we can come up with this following equation here. And so now we're going to be trying to find a relationship between I1 and I2 that will enable us to substitute for one of these variables and solve this equation. And so if we're taking a look at this 10 amp current source, we can see that there is an I1 and an I2. And so we see that I2 is flowing in the same direction as the 10 amp current source, and I1 is flowing opposing it. So that means that I2 minus I1 equals 10. We can say this because we know that the current in this branch is 10 amps. It's an ideal current source, and so it's going to enforce that. And so we can use the defined mesh currents to come up with this relationship here. And so if we plug this relationship into equation 1, we can get this equation, and we can solve for I1 as negative 6.73 amps. And so if we remember that VA is just 15 I1, just looking at the current flowing through this resistor here, that comes out to negative 100.9 volts. And so that's the answer that we expected, and it's good that we got that answer. So does anyone have any questions?
Where exactly did the equation 1 come from?
So equation 1 came from, we wrote KVLs around the 3 meshes, and then we began substituting in. So the voltage across the 10 amp source is also in the second equation. And so if we move the voltage across the 5 amp source and the voltage across the 40 ohm resistor over to the other side, we can plug it in for this term here. And then we also plugged in for the voltage across the 5 amp resistor here. And
so the VA is 15 I1 and the V40 is 40 I2. Okay, thank you.
Okay, so now we'll move on to the second example, which is a previous exam question. So I'm going to stop the recording.